So in this video, we want to look at the chain rule. So the chain rule is kind of the last piece of the puzzle we need here. With this, we really should be able to take the derivative of pretty much any function. Okay, using everything we've learned up to this point plus this one. So one thing you may have noticed here is we've kind of been avoiding composition functions. So something like e to the 2x, for example, or maybe the natural log of x squared plus 1, or maybe the square root of 3x squared plus 1. Okay. So all of these functions we could write as the composition of two functions. So let's take h of x, for example. So h of x we could write as the square root of, let's say that h1 of x is the square root of x, and h2 of x is 3x squared plus 1. Then h of x is h1 of h2 of x, right? So we can write this in terms of a function composition. And remember, function composition is not necessarily commutative, right? If we do it in different orders, we might get something different. So let's look at some more general functions first, and we'll come back to these three specific examples here. So let's just look at some other h of x, which is equal to f of g of x, okay, which is also written like this, right? F of g of x. Then the derivative h prime of x is given by f prime of g of x times g prime of x. Okay, so it's like the derivative of the outside times the derivative of the inside function. Okay, so this is often written with the Leibniz notation. Specifically, the way that it is sometimes written is that if y is equal to h of x, as usual, right? And then in this case, y is equal to f of u, where u is equal to g of x, right? So we're just using basically what we call an intermediary variable. So we just let g of x be equal to u here just to make it easier to write. Then the derivative of y with respect to x is equal to the derivative of y with respect to u, because y is a function of u, times the derivative of u with respect to x, which would make sense with this last equality right here. So this is kind of where the Leibniz notation kind of starts to show its nature, right? This, if we thought of these as fractions, we think of like the du's as canceling out, and we're left with dy over dx. Okay, so this is actually one of the biggest reasons why this notation is used, is because of the chain rule. And then you can extend this out to more functions as well. So I want to focus mostly on how to use it here, because, you know, as the functions get more complicated, we're pretty much always using the chain rule on them. So let's go ahead and look at some examples here. So we'll look at the examples we already wrote out. F of x equals e to the 2x. So f prime of x is going to be basically the derivative of e to the 2x times the derivative of 2x, is how the chain rule would put this. Okay, so In other words, if we rewrote this as g of x equals e to the x, h of x equals 2x, then f of x equals g of h of x. So you would do the derivative of g of h of x. So in other words, the derivative of e to the x, and then you put h of x in there, times the derivative of h of x, which is this part. So this is what we have here. So this is like doing the derivative of e to the 2x while kind of ignoring the fact that this is 2x, just treating it as if it was just e to the x. So it's just going to be e to the 2x because the derivative of e is itself. And then we times it by the derivative of the other part, the 2x. So times 2. So in other words, this is 2e to the 2x. Okay. Okay, so now we'll look at one of the other ones we had. Natural log of, what was it, x squared plus 1. Okay. Natural log of x squared plus 1. Okay. So we're going to do the, and then we said this was g of x. Okay. So g prime of x then is going to be the derivative of the natural log part, which is 1 over x squared plus 1, right? The derivative of natural log of x is 1 over x. So in general, this is 1 over whatever's inside of here, times the derivative of the inside part. So in this case, 2x. Okay. So this is going to equal 2x over x squared plus 1. Okay. All right, now the last one we had written down, h of x equals the square root of 3x squared plus 1, I believe it was. Something similar at least. So h prime of x is going to be, it's like we're just thinking of this as if it's like the square root of x first, and then taking the derivative of that. You can even kind of think of it like you're doing a substitution, like u equals 3x squared plus 1, and then you're taking the derivative of the square root of u. Okay. So when you do that, you would get 1 over 2 times the square root of all this stuff. And then you times it by the derivative of the inside. So 3x squared plus 1, the derivative will be 6x. 6 divided by 2 is 3. So this is 3x over square root of 3x squared plus 1. Okay. So it's like you're doing the derivative of the square root of u, which is 1 over 2 root u, but then you have to multiply by u's derivative. Okay, so that's kind of what I was trying to get at with the notation up above, right? So the derivative of h with respect to u times the derivative of u with respect to x. Okay, so definitely try a lot of these. Practice with these. This is, like I said, kind of like the final hurdle. Like once you can do the chain rule, you can basically take the derivative of anything. Okay, let's do some more here. So f of x equals x squared minus 2 cubed. Okay. And then f prime of x, we're going to do the power rule on the outside. So 3x squared minus 2 squared, and then times the derivative of the inside, which is 2x. So you can always simplify these. So we get 6x, x squared minus 2 squared. Okay. Okay, let's do a couple now where we have to combine things. let's find the derivative of x over 3x plus 2 to the fifth. Okay. So f prime of x here, we're going to do the derivative of the outside, 5 times x over 3x plus 2 to the fourth. And now we're doing the derivative of the inside part, which is going to require the quotient rule. Okay, so this is a whole big thing. So the quotient rule will say this is 1 times 3x plus 2 minus x times 3, so we'll just say 3x, over 3x plus 2 squared. Okay, and then you can cancel these out. So there's different ways you could simplify this one. But, you know, the point is that we had to use the quotient rule in addition to the chain rule here. Okay, now let's look at an example where maybe we have more than 2 terms, because we can expand this out to more than 2 terms. And when I say 2 terms, I don't mean terms. I mean when we could write it as a composition of more than 2 functions. So let's look at sine of cosine of 4x. Okay. So f prime of x here, we're going to take the derivative of the outside part, which is cosine of cosine 4x, and then we're timesing it by the derivative of cosine of 4x. Okay. So this is cosine of cosine 4x times that derivative now, which is negative sine of 4x. And now we're multiplying that by the derivative of 4x, okay, which is going to be 4. So we just want to take it piece by piece and keep taking the derivatives of the inside parts. So there's not really a good way to write this, so I'll just leave it like this. But yeah, so cosine of 4x times, we could say negative 4 sine of 4x. Okay. Now let's come back to one I wrote out a while ago, x to the x. Okay. So I kind of started it. I showed the trick of how you would do this. You'd start by rewriting it as e to the natural log of x to the x. So this is a somewhat common trick, is that you write it as e to the natural log of something, because that allows you to now bring that exponent down, e to the x natural log of x. Okay. So now we can go ahead and take the derivative of this using the chain rule, right? So this is actually a little bit different from the common way of doing it, but I think this will still work. Let's just go ahead and try it out. So this is going to be e to the x natural log of x times the derivative of x natural log of x. Okay, so we need the product rule for the inner part. So this is e to the x ln of x times the derivative of x is just 1, so natural log of x, plus the derivative of natural log of x, which is 1 over x. Okay, so these cancel and we just have 1. So this is e to the x natural log of x times natural log of x plus 1, and e to the x natural log of x, we can write that back into the x to the x form. So this is x to the x times natural log of x plus 1. Okay. So, and I mean, while we're doing it, I can show the other way that this one is typically done, because it shows another trick that we can take for derivatives. It's not as common, but it is useful sometimes. It's really kind of equivalent to doing it this way. It's just a somewhat easier way to write it. So usually we use the y notation for it. If we have y equals x to the x, then we take the natural log of both sides first. Natural log of y equals natural log of x to the x, which is x natural log of x. And then we take the derivative of both sides. So when we do this on the right side, it's straightforward enough, right? We just get the same thing we got before. The left side uses, it's again using implicit differentiation, which will actually be the next video topic. So again, getting a little bit ahead of ourselves, but this is going to be y prime over y, and we'll show that in the next video. So then we would multiply both sides by y, and y is just equal to x to the x, as stated in the original problem. So we get y prime equals x to the x, natural log of x plus 1. Okay. So it's really, these are just two of the exact same ways to do it. It's just, sometimes easier to see that you can take the natural log of both sides rather than rewriting it using the e to the natural log of x kind of trick. But ultimately they are the same thing. Okay.